It's Paul with the second of 3 videos designed to replace the lecture that was lost to the bomb threat. And the topic of this one is Gateaux and Frechet differentials. Gateaux and Frechet were both active in the early 20th century. Gateaux died young, Frechet lived to a very ripe old age. What they did was to extend the concept of derivative from Rn to infinite dimensional vector spaces. And I hope that you have a reasonable understanding of what it means for a function to be differentiable in Rn. It means more than just having partial derivatives. If the directional derivative is a linear function of the partial derivatives, then the function is differentiable. And that idea generalizes to the Frechet differential, which we're actually not going to need. The Gateaux differential, on the other hand, is just a generalization of the concept of directional derivative, which in turn is a slight generalization of partial derivative. I'd suggest that you review this subject. If it's totally unfamiliar to you, you might actually want to stop in this week at the Math 23 lectures or watch the lecture videos. The class meets from 2:30 to 4 in Hall A. So, we're considering some transformation from space X to space Y. The codomain space Y has to be a norm space because we need to be able to take limits. The domain space X doesn't need to be normed if all we're doing is defining a Gateaux differential, because this is the concept of directional derivative extended to spaces that might be infinite dimensional. What it does is to take an increment vector, which I will denote by h. In R, it would just be a number. In Rn, it would be a vector of n components, but in the spaces we're interested in, it's going to be a function h of t. And we say that a function is Gateaux differentiable if the following Gateaux differential exists. We take t evaluated at x plus alpha times h. We subtract off t evaluated at x. We divide by alpha, take the limit as alpha goes to 0. This is plain old simple single variable calculus, and the result depends on 2 variables. It depends on where we evaluate the differential, that's the point x, and it depends linearly on the increment, which is h. Even if the limit exists, the Gateaux differential is not guaranteed to be a linear function of h, however. If it is a linear function, then we have a Frechet differential, and the idea of the Frechet differential is a generalization of the definition of the derivative in Rn. You take t of x plus h and subtract off t of x, and then you approximate that function by the linear function delta of t evaluated at point x on derivative h. If when you divide by the length of h, that's why we need a norm in the space x in order to define this, if you divide by h and then let h approach the 0 vector, if this limit approaches 0, we say that the function is Frechet differentiable. If we want to focus our attention on the linear transformation itself, we can say that is t prime of x times h. In the finite dimensional case, t prime of x is going to be a matrix which represents, as you know, a linear functional. And the matrix in question is the Jacobian matrix, which you've undoubtedly heard about in studying multivariable calculus. In the infinite dimensional case, there is no such matrix, but you'll see in a minute that sometimes these differentials can be represented by functions. This is a bizarre definition, so let's try a couple of examples. We're going to use the definition to calculate a Gateau differential. And I'm going to start with a nonlinear functional. Take a function x of t, square it, integrate from 0 to a with respect to time, and you've calculated a real number. So that's a function of x, where x is the function of time, x of t. Now let's use the definition of the Gateau differential. It says, take f of x plus ah, subtract off f of x, divide by alpha, and let alpha approach 0. Sorry, this is also an alpha, not an a. Well, let's plug in the squaring function for f of x plus alpha h, plug in the squaring function for f of x, expand this. The terms in x squared are going to cancel out. What we've got left is the cross term 2 alpha times x of t times h of t, plus another term alpha squared h squared of t. We have to sum those, integrate over t from 0 to 1. When we divide by alpha, we can cancel that alpha against this power of alpha, cancel it against 1 power of alpha here, leaving a term that's clearly going to go to 0 as alpha approaches 0, and we've got our answer. Our answer is that the Gateau differential evaluated at x, where x is a function of time, on the vector h, a function of time, is the rule take 2 times x of t times h of t, multiply and integrate from 0 to 1. This is clearly a linear functional in h. In that case, we can say this is the capital X prime of t, and since the functional is linear, it's also the Frechet differential, and this is the Frechet derivative. So you can see what's going on. When we calculate the Gateau differential, we are getting the usual sort of linear functional, which is multiply two functions and integrate. Let's try another one. This time I'm going to let x be the space C0, 1, and I'm going to assume that I have a function of x and t, two variables, which has a continuous partial derivative with respect to its first argument. I'm going to denote that partial derivative by g sub x. This is standard notation in this context, rather than writing partial of g with respect to x. So now I can define a nonlinear functional. I take x of t, a vector in this space, a continuous function, plug it into the function g, integrate over t from 0 to 1. That's my f of x. And here's the definition. I evaluate at x plus alpha h. I subtract off the value evaluated at x. And now, in order to do the first term, I need to do a little bit of approximating. For any specific value of t, this is just a number, that's just a number, and the value of g, as long as alpha h is small, is nicely approximated by alpha h times the partial derivative with respect to the first argument, this argument, evaluated at x of t and t. This is not exact, but the other terms will have alpha squared, h squared in them. In general, they will be terms that have the property that when I divide by alpha and take the limit as alpha goes to 0, they go away. So what survives? This alpha cancels that alpha, and all I'm left with is the integral from 0 to 1 of the partial derivative of g with respect to its first argument multiplied by h. Again, this is a linear functional of the function of the vector h of t, and it's represented by this partial derivative of g. Now, what has this got to do with extrema? Well, we're looking for relative or local extrema, and let me remind you what a local minimum is. We have a local minimum of the function f at the point x0 if nearby f of x is never less than f of x0. It can be equal. And by nearby, I say some open ball containing x0 has to have this property. Now, if you're fussy, you say, what are you doing talking about open balls? You said for GateauxDifferentials there didn't have to be any norm defined in the domain space capital X, and aren't open balls used to define norms? Well, they are, but this ball is only being used to specify an open set. Leuenberger carelessly refers to this ball as a sphere, but the sphere is actually the boundary of the ball. Modern usage would have ball where Leuenberger used sphere. So we really don't need a norm in the domain. I can define relative maximum in an obvious similar way, and then extremum means one or the other. That's my phone ringing in the background, but I'm not going to answer it, and I'm not going to edit it out of this video either. So, what I want to prove for you is that a necessary, though not sufficient, condition for an extremum is that if the Gateaux differential exists, it has to be 0 for all vectors h. Let me remind you of the key theorem of single variable calculus. We've got a differentiable function g of t. If it's differentiable at t0, its derivative is the slope of the tangent line. And it's pretty obvious, I'm not going to take the trouble to prove this, that if the derivative exists and is either positive or negative, we can't have a local extremum for the simple reason that if the derivative is positive, there are larger values on this side and smaller values on that side. If the derivative were negative, there'd be larger values here, smaller values there. So neither the condition for a local minimum nor the condition for a local maximum can be satisfied. So remember this result from your first calculus course. If the derivative exists at x0 and is non-zero, we can't have an extremum there. We've been using that in dealing with those crazy functions that were sums or maxima of absolute values of first degree polynomials. Another way of looking at this, a local extremum at x0 requires one or the other of two things. Either the derivative exists and is 0, or the derivative doesn't exist. Now, how does that apply here, where we're talking infinite dimensional vector spaces? Well, g of alpha is just a function of a function that produces a real value. It goes from some subspace in our domain space X to the real numbers. And the Gateaux differential, written in the language of single variable calculus, is the derivative with respect to alpha of this function of the real variable alpha evaluated at alpha equals 0. That's the calculus way of saying divide by alpha and then take the limit as alpha approaches 0 of the resulting function. So this is g prime of 0. And let's consider the requirement. If this Gateau differential exists, it has to equal 0. A word of warning. Let's try applying this function to the function of two variables f of u and v is equal to u times v. In that case, the Gateau differential with respect to the first standard basis vector is equal to v. With respect to the second standard basis vector, it's equal to u. Those are the two partial derivatives, and both those partial derivatives are equal to 0 at the point whose two coordinates are 0. But, as I trust you know, f doesn't have an extremum there. It has neither a maximum nor a minimum. It has a saddle point. That's okay. All I said was that having the Gateau differential equal to 0 at x0 is a necessary condition. It's definitely not a sufficient condition. Okay, with that introduction to Gateau differentials, I'm going to bring this little video to an end and resume with the final video, which will derive the classic Euler-Lagrange equations of the calculus of variations.